Okay, thank you, Professor Nandakumaran, for not supporting me and for inviting me here. My talk is on asymptotic study of locally periodic oscillating domain. It's a joint work with Professor Klaus Petersen from University of Tromsø, Norway. So I'll start with what is rough domain, which we have been seeing all the time. Then I'm going to just put Laplacian on the locally periodic oscillating domain and try to find the limit using unfolding, of course. And then I'll explain what are the unfolding operators which are related to our work. Then I'll state the result if possible. I'll try to prove some. This you have seen, it's a heat radiator. The chemistry guy knows. And then it's another heat radiator you see in your CPU. Why I'm saying these are the motivation to look for oscillating domain. This is a jet engine where you have the oscillating boundary part. Again, same thing, you have a fixed part and oscillating part. You want to pose a problem in this domain and then study as epsilon tends to 0, where the solution goes, what is the limit, what is the equation, all these things. Why do you want to do? Because if you want to do some numerics on any problem posed on this domain, this is going to shrink when epsilon goes to 0. Then if you want to discretize, for example, for FEM method, then you have to take your H discretization, whatever, the length very smaller than the epsilon, which is very complicated and very costly problem. So you want to get out of this oscillating domain, go to the fixed domain, try to solve your problem. Right? So this Abu explained, Professor Nandakumaran explained already. So we'll go to, this is my domain that I'm going to consider. This is, I call it locally periodic domain because there is no periodicity in this. This can behave any crazily. I'll explain mathematically what the domain is. So my aim is to pose a problem on this domain omega epsilon. And since the domain is depending on epsilon, so your solution is depending on epsilon. So as epsilon tends to 0, you want to study your solution behavior at 0. So this is my boundary of the domain where eta is a strictly positive Lipschitz function defined on 0, 1 times t. T is the torus, one-dimensional torus, means eta is periodic in the second variable with 1 periodic. So using this, you define the locally periodic oscillating domain. I think, up to my knowledge, this is the first time we deal with locally periodic domain. This is the problem that I'm going to pose. It's a simple Laplacian with homogeneous Dirichlet condition on the fixed part of the boundary and a Neumann condition, homogeneous on the oscillating part of the boundary, where gamma is given by the base of the domain. In the other places, you put Neumann condition. So this is the limit domain. This also looks like oscillating, but it is independent of epsilon, because of the choice of eta, it looks like this. So this limit, we have to give what are the boundaries and interface. So this part is the fixed part. There is no oscillation in this below the dashed line. And the above part is the one which has oscillation. So, before this work, Professor Gardello and Mura and Gube did a work where they have the interface is non-flat. Other than these two, I think no other work where you see oscillating domain problem with non-flat boundary. And I will define the boundary of this limit domain. So define eta minus as a minimum of eta of x1 y, where x1 is fixed. For each fixed x1, you look at the minimum, and that is eta minus, and eta plus is defined as the maximum. Using these, so since eta is Lipschitz function, eta minus and eta plus also a Lipschitz function, you go back, so this is given by eta minus, this is given by eta plus. Now the domain is fixed, so no problem for the numerical people to do the problem. Now what is our aim? So we have a problem which is depending on epsilon. You want to find a problem which is independent of epsilon defined on this domain. Right. So Okay, in omega minus, there is no trouble because there is no oscillation. So we don't have to worry about at all in the omega minus because you have the compactness result, you can pass to the limit, get the equation. In omega plus, since it is oscillating, you need something to do. So why it is difficult? Because if you start with the zero extension, you lose the compactness results. So it's not possible. So if you want to do extension, for example, the domain is oscillating. It is changing when epsilon is changing. What is the meaning of convergence of U epsilon when it is defined in different domain? So either you have to do an extension or some other thing. So we are going to do it with the unfolding operator. What the unfolding operator is going to do is, okay, it's going to do, it takes a function which is defined on omega epsilon, which is oscillating domain, to a fixed domain. So in a fixed domain, you can do all the operations, get results. Then you come back to the fixed domain using some arguments. That's the idea. Okay? Right. So now I'll explain what is the limit problem. So here H denotes y of x. So eta, you know, this is the function we used to define our oscillating domain. So we call this is a reference function. So y of x is called a reference set. For each x1, x2, you define a set, which is this in this way, and we'll look at the measure that's defined by h of x. In omega minus, it is always h equal to 1. In omega plus, it will change accordingly how the geometry of eta, it depends on the geometry of eta. Okay, here we are not assuming the upper part is flat, all these things, because we know how to control now. So in earlier, if you look at the Bidan's work, Abu's work, so we assumed that the upper part is flat, so that h is positive everywhere. So there is no issue. Now we assume nothing on this, so it can go to 0 at the top of the domain. So only thing is that the solution may not be in L2, it may be a very rougher than the L2 space. Okay, so you know H now. Using H, you define a Lebesgue space. You look at this V, set of all V, such that we integrate it with respect to this H dx measure here. So this is your L2 space, and using this, you define a W omega space. Here is where your solution is going to be. Okay. So in this W omega, you define a Hilbert inner product. Using this, you can show that this is a Hilbert space. Once you have a Hilbert space, you can easily talk about the solution or solution of at least Laplacian or this linear problem. If you can relate this weak formulation with the inner product. Okay, so now we are okay with the limit space. Let's go to the limit problem. So limit problem is in this way. So A0 is capturing what happens in the upper part, lower part, all these things. A0 is given by this. Okay, this might look complicated. So let's go to weak form, then you will understand. So weak form, it can be written as A0 grade U0 grade phi. If you rewrite it, this is what the limit equation is. Which means in omega minus, you get the same Laplacian. In omega plus, as usual, there is an oscillation in the x1 direction. So the derivative in the x1 direction gets averaged out. So you get this one in the upper part. Okay. Now, if you look carefully, this is nothing but the inner product of the space that we have defined. So directly without any work, you get the existence of the weak solution of this problem in W omega gamma. Here gamma represents the base part where the function is 0, right? Okay, so what you want to prove is that, so you have a U epsilon, which is the solution of your non-homogenized problem, and you want to say 0 extension of this goes to h times U0, and 0 extension of the gradient goes to A0 times grade U0, where h is defined as the measure of the reference set that we have defined. So the main idea is not to just prove this theorem, just to first understand how to handle this locally periodic thing. Okay, so what the tool that we are going to use is, of course, unfolding operator. Okay, what is this? Okay, this is the weak form of the Laplace equation, where you have you are going to find U epsilon in H1 omega epsilon gamma. This means the set of all function in H1 omega epsilon, which is 0 on gamma. So this is true for all C in H1 omega epsilon gamma. So here also existence, prior estimate, all are direct. So we have the prior estimate in H1 omega epsilon independent of epsilon. So okay, now so once you have this, now you want to use some operator, either unfolding or any other thing, or extension operator to do this problem. We will use unfolding. So we have been seeing this unfolding for the last 2 weeks. I don't want to go into this now old unfolding for the fixed domain. So this was introduced by Siransky, Damlamy, and Griso in 2008 to study composite materials in periodic setup. So then it was used for perforated domain by Professor Donato and other people. So what we are interested in is the oscillating domain. Okay. This has nothing to do with, this looks very too different from what we are interested in. But so this is called oscillating domain. Now this is fixed part, this is oscillating part. So what for this they defined an unfolding operator to study the homogenization by Blanchard, Gardello, and Griso. Okay, so look at the upper part. In the lower part you don't need any extension operator or any other operator because of the it is fixed. You have the compactness result you can do. In the upper part there is an oscillation in x1 direction. Since there is oscillation in only x1 direction, the unfolding will be only in x1 direction. So this is what they defined. I'll explain little later what is the unfolding operator for this domain and subsequently what we have done and so on. So after the introduction, Damlamy and Peterson used this to study elasticity problem and so on. And then they, for the Laplace equation, they try to give character result using unfolding. And then Nandakumaran, Prakash, and Sardar used this unfolding operator to study optimal control problem with periodic control acting on the upper part of the domain. Okay, in this work, they not only used unfolding operator to study the homogenization, but also used it to express the optimal control in the epsilon level using the unfolding operator. Okay, and the next work with Sardar, we studied biharmonic equation in this domain, and we put Dirichlet Dirichlet control on the oscillating part and used unfolding operator to get the limit optimal control problem. So, okay, now I want to explain what was the unfolding they did. So the domain, if you look, you look at, this is my reference cell, okay? So this is your P. This is P, this is Q. So when you look at any point here, x1, x2, you look at any point in the oscillating part x1, x2. So you don't have to worry about x2 variable because there is no oscillation in the x2 variable. So x1 can be written as epsilon times x1 by epsilon plus epsilon times y, where y belongs to, can y belongs to 0, 1? Can we take y from 0, 1 so that it will be still inside the domain? Here it is epsilon p and this is epsilon q, this. So we have to take y from pq. Then only this x1 will be inside your oscillating domain. Understood? If you take y from 0, 1, suppose, then it will be outside the oscillating domain, but you just want to know what happens inside the oscillating domain. Okay? Using this, what they did, so choosing this y is very important here. Okay? So the unfolded domain is defined like omega plus times pq. Omega plus is h1 to h2 times 0 to 1. Or 0 to 1 times h1 to h2, and pq is this. So how do they define? You take a function which is defined on L to omega epsilon plus epsilon, omega epsilon plus 2 L2 omega plus times AB. So unfolding operator take a function which is defined on this, takes to here. How it is defined? You take a function T epsilon phi of x1, x2, y, which is equal to phi of, I have 5 minutes, epsilon, x1 by epsilon, epsilon y, comma x2. So there is no, we are not touching the x2 variable, just only happening here, and it is defined. So what I want to say is, once you fix the unfolded domain, omega epsilon plus times AB, then the same unfolding operator which was defined by Sharansky-Damlamian, you can use it in one direction, you get this everything. So you don't have to do anything. What you have to do is just need to understand what is your unfolded domain. Okay? Okay. So what is the main thing you want to do when you define unfolding operator? You want to look at the integral equality, because your function is defined on omega epsilon plus. So when you look at the weak form, it will be integration on omega epsilon plus, but unfolded thing will be in the omega u, right? So this is what you want to look at. Okay, since I have 5 minutes, I don't want to go into this. I have to go to my problem. So this is so mainly you have to fix somehow this unfolded domain. So you can get this integral equality. This is our next work. I think I will not go into this again. Here what we did was, we defined, we looked into this domain into union of several oscillating domains. First you look at only this part, this we call it omega 1 epsilon, and look at only first branch on each part of this one, this much only, this much, and that is omega 2 1 epsilon, and only look at this part and 2 like this. We just divided this domain into different parts. For each part we defined one unfolding. Using that we expanded the domain to different unfolding domains and studied its limit, so that you get to a limit in a multi-sheeted function space. It was introduced by the Ukrainian mathematician Melnik. So we used the same idea, but using unfolding. He did a problem with asymptotic expansion method, which was very complicated for us, at least for me. So with unfolding, it was very simple, and we get the limit. We studied a parabolic optimal control problem using this, and we were able to explain the control in each layer and each branches, the contribution of each layer and each branch using the multi-sheeted function. Okay. Okay. Next, we'll go to another. Yeah, this is what Abu was explaining a control problem. In this, what we did was okay. Now this domain is not made up of this type of thing, but it is made up of something like a reference cell. It's like you take a reference cell like this. Okay. Using this, you define that periodically. So now you cannot take this PQ in place of omega there. So because it is not fixed everywhere. Now you have to change it when for each x1 you have to change. For each x2 you have to change. So for that, what we did was we defined what is called a reference set. What is called reference set. So take any element T, look at this line, look at its projection on x1 axis. This is called y of t. We define like this. This is the reference set. Using this, we defined unfolding. That is simple. You just take omega plus times y of x2. This is our unfolded domain. Using this, now everything same unfolding. The unfolding is same, except that y belongs to this set, which is changing when x2 is changing. Okay. This was the idea of defining unfolding for this type of domain. So in this work, we studied a semilinear problem, no control. Semilinear problem using the unfolding, we got the limit behavior. Okay, in this paper, we assumed that the top part is flat, so that you have no issue. But then, this is with Ravi, Nandakumaran, and Rajesh. They used this unfolding to study another problem with non-linear boundary condition on the oscillating domain, in the same domain where they used. And then in this work, yes, in this work we studied a semi-linear optimal control problem where we don't assume h equal to 0. That means we are not assuming this thickness of this goes to 0. We assume it can go to 0. We are not assuming it to be flat, but still we are able to characterize the limit equation. And this is what Abu explained. Okay. So in this paper also, we have, okay, we used the same idea in the polar coordinates and defined unfolding operator in polar coordinates, used this to study a elliptic problem in this domain and get limit equation in the same paper. And with Editha, Ivy and Nandakumaran, we have studied an optimal control problem in this domain. Okay. Okay. The next work was okay, kind of motivated by Professor Onofrei's idea when we met in Philippines. So what you do is you divide your domain into mesoscales. In each mesoscale, you put a different periodicity. Okay, it is of epsilon order, but with some constant multiple of periodicity. It's not fully periodic, but not fully locally periodic. It is in between something. So in this, again, we defined an unfolding operator. Using that unfolding operator, we studied the limit behavior. Okay, now what we did, there was some domain of this rectangular, then we extended to different branch thing. You understand in different layer, that was finite case. Then you go to the uncountable changes in x2 direction, you go to a smooth domain. Then, okay, we are okay with periodic, now you go to locally periodic. So fully periodic we didn't understand. So sorry, fully locally periodic we didn't get that time what to do. So we thought, okay, this may be the next step to do. So we did unfolding here. Then we came back to the non-periodic setup. So unlike the earlier setups, I was telling you, there is no change in the unfolding operator. Only there is a change in the unfolding domain, unfolded domain. So you have to somehow find the unfolded domain for any problem you are dealing with in periodic setup. So the same unfolding. Now the unfolding that I am explaining is for the locally periodic, the problem that we are currently worked out and completed, submitted. So the same unfolding you use. 2 minutes. Okay, yeah, we can complete in any minute. Okay, omega epsilon plus is the same that we have. That means you just look at the upper part. And I define an unfolded domain. This is not the fixed domain. In earlier cases, unfolded domains were fixed. Now this is an approximate unfolded domain. This is omega minus, you apply unfolding on eta minus function and apply unfolding on the upper boundary. Then this is a domain, omega u epsilon. This is approximate unfolded domain. Okay, what it has is, if you apply omega epsilon plus, if you apply unfolding, this is what you get. Okay. And it converges to omega u strongly. Omega u is a fixed domain, which is used eta minus and eta. Okay. So okay, we are not able to unfold our problem to a fixed domain, but it is very near to a fixed domain. There we do all our problem. So as I was saying, we need that unfolding criterion for unfolding operator, which we have given here. With when you take a function in V in LP, then you have this error, and when you have L1, then you have small order of 1. Once you have this, then everything is similar, except the Thatha's oscillating test function you have to use at some point of time, which is okay for a periodic case, but it's not okay for non-periodic. But okay, so once we have this lemma, then what do? You just take your problem, a weak problem, and apply unfolding, and use your a priori estimate, pass to the limit. Now you have to find what is P. Other things you know. Now you just need to see P. To find P, you need to use Thatha's oscillating test function. But here you cannot use the same oscillating test function. So we came up with a different test function which works for it. Using this, you can characterize P, which is the mean of P in each y of x is 0. Now you know everything like u0 and p, then you just put it in the equation, you get your limit equation. This is your limit equation that we have explained earlier. And also we proved that T epsilon of E epsilon, that means unfolded function, converges strongly in the unfolded domain. And also the L2 strong convergence of this thing. Okay? So it's a simple proof, just energy convergence stuff. With that, I stop. Thank you.
Okay.